All right, we're going to go ahead and move on to section 2.1, which is all about kind of rethinking, we'll say, about our trig function values in terms of the actual sides of the triangle versus x, y, and r. Okay, so we're going to go ahead and focus on acute angles, okay, and that's what we're going to make our reference triangles with all of the time. All the time. So we're going to rename these sides. If I have this angle that's in standard position here, and obviously it's acute, right? It's less than 90 degrees. Instead of thinking about this as x, y, and r, normally with a triangle, the longest side is the hypotenuse, right? Hypotenuse. So we're going to label that as our hypotenuse. Notice there's a side that is completely opposite the angle, right? Or however wide this angle opens up, this is the side opposite it. So instead of y, we're going to use opposite. And then this side, which we normally would call x, because it's in standard position here, we're going to call this the adjacent side because it's adjacent to our angle theta. Okay, so same way that we defined our trig functions before, except now instead of using x, y, and r, we're just going to say opposite, adjacent, and hypotenuse. Okay, so instead of defining sine as y over r, we're going to define it as opposite over hypotenuse. And there's a fun way to kind of remember this. If you just take the first letters, sine is opposite over hypotenuse. I like to write it as S is O over H, like that. Same thing with cosine. Instead of saying x over r, we're going to say adjacent over hypotenuse. So cosine is A over H. And then tangent, instead of saying y over x, we're going to say opposite over adjacent, right? So that would be T is O over A. So notice if I made little words out of this, it kind of looks like Sokatoa, which kind of sounds like a fun little Indian language, right? Sokatoa. But it helps us remember sine so is opposite over hypotenuse, cosine ka is adjacent over hypotenuse, and tangent toa is opposite over adjacent. So if you can remember Sokatoa, you should be able to come up with the first three, which is a little bit easier than remembering x over something, y over something, y over x, x over y, right? And then if we can remember the order of those, then in order to do our reciprocals functions, we just flip them, right? All right, so let's look at practicing with that new way of labeling. Okay, so here is a triangle, right? And notice they want us to find all 6 trig functions for both the angle G and the angle F. Okay, so I'm going to look at G first. So that means we're looking at this angle right here. So I want to go ahead and label my triangle. If I'm looking at this angle G, the side that's completely opposite, or that my angle opens up to, is this length here of 8. So this is my opposite side, right? The one that's adjacent to my angle, 6, this is going to be my adjacent side, right? And then the longest side of the triangle is my hypotenuse always. Hypot, right? And we can see here, this is the 90-degree angle. So let's go ahead and start labeling these in terms of our sides. So if I want sine of G, remember sine is so in our Sokatoa, so that's opposite over hypotenuse. So if I look at the side opposite G, that's 8 over my hypotenuse, which here is 10. Okay. And then we do want to go ahead and reduce. In my math lab, we always want to make sure our fractions are reduced, or if we end up with a radical, that we rationalize the denominator. Okay, so this is going to reduce down to 4/5. And we want to do the same thing with cosine. Cosine is our ka in our Sokatoa, so adjacent over hypotenuse. So our adjacent side is 6, and our hypotenuse is 10. So we get 6/10, which then we can reduce down to 3/5, right? Okay, and then I'm going to go ahead and do those inverse trig functions or trig values next, because since I already know what the sine is, I can just flip it to get the cosecant, right? Because those two are inverses. So if sine g was 4/5, then cosecant is going to be 5/4, right? And then secant g is the inverse of cosine. So now that I know that cosine is 3/5, I can just flip that and get 5/3 for our secant value, okay? Then for our tangent, I'm going to go back to our little shortcut, our SOHCAHTOA. Our tangent is the TOA part of it, so opposite over adjacent. So our opposite side is 8, our adjacent side is 6, so that gives me 8/6, which then reduces down to 4/3. Okay, and then now that we know what tangent is, we can easily get cotangent just by doing the reciprocal. So this becomes 3/4. Okay. All right, so not too bad. We've already done trig function values before. All right, got a watery eye. But now what we're going to do is find them of more than one angle within that triangle. So now I want to find the trig function values for F. Okay, so I'm going to use a different color pen. So now we're looking at F. Okay, so when we look at angle F, notice F opens up to this side, which would be its opposite, right? This is the side opposite angle F. So now this is going to be my opposite side. The side that's adjacent to F is going to be this length 8. So this is now my adjacent side. And then notice this is still the longest length of the triangle, so it is still going to be my hypotenuse. Okay, so now that I have it labeled for angle F, I can go ahead and find all the trig function values for F. So I'm actually going to let you do that. So go ahead and pause the video and see if you can fill in all of the trig values for angle F. Okay, if you get stuck or if you finish and want to check yourself, unpause it and we'll see how you did. Okay, let's see how you did. When we're looking for our sine, that's our opposite over hypotenuse, which here should be 6/10, right? Because this is our opposite side, this is our hypotenuse side, and we reduce it down to 3/5. And then once we know what our sine function value is, now we can go ahead and find our cosecant, right? By just flipping that. Then we find our cosine, which is our adjacent over hypotenuse, which using my pink labeling here would be the 8 length over the 10 length, which reduces to 4/5. And then again, once we know what cosine is, then we can do the reciprocal to find cosecant, right? Tangent is TOA, or opposite over adjacent. So that gives us opposite over adjacent is 6/8, which reduces down to 3/4. And then we just flip it to get our cotangent value. Okay, so maybe not so bad, right? Learning new things, but still just finding the trig values, which we've done before, right? Just labeling them a little bit different. So one thing that I want you to notice is some similarities that you might have seen when you were working through this. If I look up here, notice I have the sine of G, I got 4/5, right? And then over here, I also got 4/5 on cosine F. So I'm going to write down here, I got that sine G is equal to cosine F, right? Or in other words, these two gave me the same value, right? If I did sine G and cosine F, I got the same thing, right? Or vice versa. Notice if I do cosine G, I ended up with the same thing as sine F. So these two are the same as well, right? So cosine G is equal to sine F. And I want to just think for a minute why that worked out that way, okay? So if I look at my triangle, notice whether I'm doing G or F, my hypotenuse side stays the same, right? The only thing that changes from focusing on G or focusing on F is how I label the other two sides that are attached to my 90-degree angle, right? If I'm looking at F, this side is opposite, but if I'm looking at G, this side is adjacent. So that's why these are opposites, right? Because the only difference between sine and cosine is whether we're doing adjacent over hypotenuse or opposite over hypotenuse, right? So that's why that works out. Now, this works out specifically for all triangles, excuse me, or more specifically, angles that are complementary. So remember when we talked about complementary angles? Well, even before that, remember how we talked about how all the measures of the angle in a triangle have to add to 180? Well, if this is a 90-degree corner, then I know that's 90 degrees, right, of the total 180. So that means there's only 90 degrees left to split between F and G. And when angles F and G add to 90 degrees, that means they're complementary. So angles F and G are complementary, okay, which means they add to 90 degrees. And this is true with all complementary angles, that the sine of one will equal the cosine of the other, or the cosine of one will equal the sine of the other. And actually it goes beyond just sine and cosine. If we go back and look at our function values, look, there's some more similarities. Notice secant here, 5/3, is equal to cosecant, right? These two are related. And same thing the other way. Cosecant of G, we got the same thing as secant of F. So this kind of provides a unique relationship where we know that if two of these values are equal, that only happens if their angles are complementary. Or if we know angles are complementary, then we know they have these properties that kind of goes along with them, right? So same thing with tangent and cotangent. Look, tangent G, 4/3, cotangent F, 4/3. So these two are related, okay? Now, instead of just leaving these X's and expecting you to remember what that means, I'm going to write it all on the next page, okay? So let's go to the next page where we have this all written out. So angle F and angle G are complementary angles because their measures, or the measure of G plus the measure of F, add up to 90 degrees, okay? So if they add up to 90 degrees, only if they add up to 90 degrees, only if they're complementary, then we have these neat relationships. Now I'm going to kind of pair them to match the X's that I wrote on the first page. So we know that sine and cosine go together. So that means that sine G is equal to cosine F. Cosine G is equal to sine F. And then we know that cosecant and secant go together, right? Cosecant G is equal to secant F, and secant G is equal to cosecant F, okay? And then our last ones are tangent and cotangent. So tangent G is going to equal cotangent F, and cotangent G is going to equal tangent F. Again, this only happens when F and G are complementary, meaning they add up to 90 degrees. Okay? If F and G are any other angles, this does not work. This is not true. Okay? Now, how we're going to use this to help us out. We're going to use this idea that they add up to 90 to be able to either rewrite like a sine value as a cosine value, or a cosecant as a secant. Sometimes we just want to rewrite it. Or we can use this idea that they add to 90 to be able to solve for what one of the angles actually is. So in other words, let me write this out. Instead of saying the measure of G and the measure of F, I'm just going to say G and F. So this means that G plus F equals 90 degrees, right? So let's pretend I knew what G was, but I didn't know what F is, right? The way that I could solve for F is I could just take that known value of G, right, and subtract it from 90 degrees. Or in other words, F is equal to 90 degrees minus G, right? So if I knew that G was, say, like 20 degrees, I could figure out F by just taking 20 degrees and subtracting it from 90, and that would mean F would have to be 70 degrees, right? So instead of writing all of these as angle G and all of these as angle F, if I already know what angle G is, then I can figure out angle F by just doing 90 minus G. So what I have written down here below is all these same identities, but instead of using an F, I just wrote it as 90 minus G, right? Because that's how we can figure out what F is we can just take 90 and subtract that known G value. Okay, so again, these are the same exact properties that I have written here. The only difference is instead of writing with instead of writing them with an F, right, I'm writing them with a 90 minus G. So I want to show you how we're going to use these to solve, and I'm actually going to keep this paper, hopefully visible, while I look over at page 3. So on page 3, it says use the cofunction identities to fill in the blanks. So I want to try to rewrite sine of 9 degrees. So if I want to rewrite sine of 9 degrees, I can look at its cofunction value, and that means that I could write it as a cosine, right? So I could write this as cosine of a different angle, right? Not cosine of 9 degrees, because 9 and 9 does not add to 90. So if I want to figure out what my other angle value is, I need to do 90 degrees minus the angle of my first, or the measure of my first angle, which we know is 9 degrees, right? So that means this is the same thing as cosine of 81 degrees. Does that make sense? And I know a lot of you are not going to have to write in this intermediate step. A lot of you probably were like, oh, well, if it's sine 9, it's cosine 81. That's totally fine. I am writing out this middle step in case you look back at your notes and you're like, how did I get that 81? Where did that come from? Okay, so this is our answer, and this is just the intermediate step, okay? All right, so let's do the same thing with cotangent. If I look at cotangent, cotangent can be rewritten as tangent using the complementary angle. So this would be tangent of 90 degrees minus whatever angle measure we have here, which is 76. So this ends up being tangent of 14 degrees. Second guess myself. Good. All right, so I'm going to give y'all just a second to do this last one. Okay, I'm going to write this as practice. Go ahead and do it. And once you've done that one, unpause the video and we'll go over it, okay? Okay, so on part C, cosecant has a complementary angle with secant, right? So I can figure out what the secant angle measure is by doing 90 degrees minus the angle measure I had for my cosecant. So 90 minus 45, which actually leaves me with 45. So that means that cosecant of 45 is the same thing as secant of 45, okay? All right, I want to show you another way that we can use these cofunction identities to solve for an unknown angle measure, okay? So I want you to think about these problems. When you see them, there's got to be some strategy, right? There's got to be something that stands out to you, something that creates a light bulb effect in your brain, right? So when you look at these, it's kind of like not normal to see, oh, look, there's a cotangent of something that happens to equal a tangent of something. Well, cotangent and tangent are not the same trig values, right? Those are inverse values. So this is odd to me to see that a cotangent equals a tangent. So the only time that you see a cotangent equal a tangent value is when you're dealing with complementary angles, okay? So what this tells me, just seeing this statement, is that these must be complementary, okay? Because that is the only time that this happens. And if this is the, let me see if I can get this to focus. If these are complementary angles, what that tells me is that they add to 90 degrees. So that's what I'm hoping to use to help me solve this, okay? Because really, whatever's inside these parentheses, we could call this F and we could call this G, right? It doesn't matter what F and G are. If they're complementary angles, that means that F plus G equals 90 degrees, right? Or in this case, my first angle measure, which is theta minus 8 degrees, plus my second angle measure, which is 4 theta plus 13 degrees, has to equal 90 degrees, okay? So even though what's inside those trig functions is kind of ugly, it doesn't really matter, because whatever this measure is, when it's added to this measure, I know it has to be 90 degrees because I know that these two angles are complementary. Otherwise, this would not even be a true statement, right? And now that I have this statement, now I can go ahead and just drop those parentheses and solve this equation. So I have a theta and I have a 4 theta, which gives me 5 theta when I combine. I have a negative 8 and a positive 13 degrees, which leaves me with 5 degrees when I combine, is equal to 90 degrees. And then I can go ahead and solve by moving my 5 degrees over, which leaves me with 5 theta is equal to 85 degrees. And then I go ahead and just divide off that 5, okay, which gives me theta is equal to 17 degrees. So we were able to find this unknown value, or this unknown angle measure, simply by using the fact that these must be complementary, okay? So same idea on the next one. When I'm looking at it, I see I have a secant and a cosecant. These two things are only going to be equal when their angles are complementary, okay? So I'm going to let y'all work out the second one. I'm going to go ahead and have you pause the video, and then when you're ready, unpause it and we'll go over it, okay? All right, so same thing on part B. Secant and cosecant are only ever equal if our angles are complementary. So if our angles are complementary, that means that they add up to 90 degrees. So I just take the angle measure from the first, add it to the angle measure of the second, and I know it equals 90. Then you can drop your parentheses and combine like terms. So we end up with 7 theta plus 6 degrees equals 90. We move our 6 over and divide our 7 off, which should leave us with an angle measure of 12 degrees for that unknown theta value, okay? Hopefully we're okay. If you need a little bit more time to look at that, go ahead and take your time, pause the video. But I'm going to go ahead and move on and look at how we can easily find trig function values for a 30, 60, 90 triangle. And then we're also going to look at a 45, 45, 90 triangle, because these are the acute angles, or the angle measures, that we're going to create these little reference triangles for, that we are going to use for the entire semester. So what we're learning in this section is never going to go away. So it's important to make sure that we know how to do it, okay? All right, so the first one is, if I want to create a 30, 60, 90 triangle, the easiest way is to start with an equilateral triangle. Equilateral triangle. And remember, an equilateral triangle has all the same lengths, right? And the same angles. So notice here, this is length 2, this is length 2, this is length 2, which I've split it up to 1 and 1, but it's still length 2. And if I know that all the angle measures have to be the same, and they all have to add up to 180, if I take 180 and divide it by 3, that means they're all 60-degree measures, okay? Now, I want to make sure I have a 30 and a 60. So what I did is I just divided this equilateral triangle right down the middle. So if I just drop a completely straight line down, I know that that's going to create a right triangle in this corner, right? And if I split this 60-degree angle completely in half, that creates my 30-degree angle. Okay. So notice I have almost all the information I need. I have this angle length, or angle. I have this length of the triangle of this side, right? I know the length of the hypotenuse, but I don't know the length of this line that I dropped down. So I'm going to go ahead and solve for that. And then once I have that value, then we should be able to figure out any of the trig functions for either a 30 or a 60, because I'll have the opposite, the adjacent, and the hypotenuse values, which is what I need to find my trig values, right? All right, so to figure out this y length, which we've labeled y here, I'm just going to use the Pythagorean theorem, right? We know that for a right triangle, if I square the lengths of the legs and add them together, that should equal the hypotenuse squared. So in other words, that means that y squared plus 1 squared equals 2 squared, right? Good old Pythagorean theorem. So that means that y squared plus 1 equals 4. And then I move my 1 over by subtracting. So y squared equals 3. Now, normally when I get rid of a y squared, I would do plus or minus when I take the square root. But I'm not going to do plus or minus here. I'm only going to take the positive square root because I know that y represents this distance, right? And a distance can't be negative. So I'm just going to take square root of 3. Okay, so that means that this length, y, is square root of 3. Okay, so I'm going to go ahead and I'm just going to rewrite the triangle over here because I don't really care about the whole equilateral triangle. I just care about the 30 and the 60 degrees. Okay, so I know that this side is 2, I know that this side is 1, and I just figured out that this side is the square root of 3. Okay, now again, if you are somebody who likes to make note cards or you have an ongoing like formula sheet study list type thing, this is something you are going to have to memorize. Okay, we need to know what a 30, 60, 90 reference triangles looks like. Okay, and there's an easy way to remember. If you can just remember 1, 2 square root of 3, that's all you really need to know. And it's easy to figure out where to label them if you know the size of these values, right? So 1 is the smallest value, right? And notice it's opposite the smallest angle. So this is my 30 degree, which is my smallest angle, right? Between 30, 60, and 90. 30 is the smallest. It's opposite the smallest value, right? 90 degrees is my largest angle measure, and notice it's opposite my largest side, which is 2. Okay, because the square root of 3 is like 1 point something, right? So it's our intermediate value. There we go. It's our intermediate value, right? Just like 60 is our intermediate angle measure, okay? So if you can just remember 30 is opposite 1, 90 is opposite 2, then you would know that 60 has to be opposite square root of 3, okay? All right, so now that we know what the triangle looks like, we want to figure out what all of these trig values are, okay? So I'm going to use some of the stuff that we've learned now so that I don't have to go through and calculate every single one individually, okay? I'm going to use my SOHCAHTOA to come up with the first 3, and then once I know the first 3, I should be able to find the reciprocal values by just taking those 3 and flipping them, right? And that will give me my inverse cosecant, secant, cotangent. And then, now that I know about complementary angles, right, and their cofunction identities, then if I know what the sine of 30 is, I should know what the cosine of 60 is. So I should be able to fill all of these in without having to use the triangle for all of them, okay? So let's start with sine, okay? Sine we know is SO of our SOHCAHTOA. So that's opposite over hypotenuse, okay? So sine of 30, if I look up here at 30, opposite 30 is 1, and my hypotenuse is 2. So this gives me 1/2. So I'm going to stop right there and see what else can I fill in knowing that the sine of 30 is 1/2. Well, I should be able to figure out the cosecant, right? Because cosecant is just the reciprocal. So if I reciprocate, I don't think that's probably the right use of that word, but if I take the reciprocal of 1/2, that gives me 2/1, right? Which is just 2. So I know that value. What else can I figure out? Well, I know that 30 and 60 are complementary, right? So I have cofunction identities. So that means that the sine of 30 is the same thing as the cosine of 60, right? So I'm going to come down here where the cosine of 60 is. I know this is the same thing as sine of 30 degrees, right? So I can go ahead and label that as 1/2. And then I should be able to find its inverse by just flipping it. So again, the secant, which is the inverse here, would give me 2/1, which again is just 2. So just by figuring out one trig function, I was able to find 4 of the values I'm looking for, right? Okay, now I will mention this. If you forget about these cofunction identities, you can figure out cosine by simply doing the adjacent over hypotenuse of 60 degrees. Because notice here, if I do the adjacent over hypotenuse, the adjacent of 60 is 1, the hypotenuse of 60 is 2, you'll still get the same answer. Okay, I'm just showing how you can work it out using those identities we just came up with. So I want you to go ahead and pause the video and come up with the remaining trig functions that are here. Okay, and then if you get stuck or if you get finished and you're ready to check yourself, unpause it and we'll go through it. Okay. Okay, so here's what we did. For cosine of 30 and tangent of 30, I went ahead and used my shortcut, my SOHCAHTOA, right? So cosine is adjacent over hypotenuse, which gives me square root of 3/2. And then I just flipped that to get my secant, right? I did the reciprocal. Now, because I ended up with a square root on the bottom, I am going to go ahead and have to rationalize the denominator for my math lab. It will not like this if we leave it like that, okay? So we end up with 2 square root of 3/3 for that one. And then I did the same thing with my tangent. I calculated opposite over adjacent. And remember, when we do this opposite over adjacent, we're using our 30-degree angle. So what is opposite of my 30-degree? 1. What is adjacent to my 30-degree is square root of 3, right? So once I have that, again, this needs to be rationalized. So rationalizing the denominator, I end up with square root of 3/3. And then I can flip it to get my cotangent. Now notice I went ahead and flipped it before I rationalized. When I had this original value here, that's what I flipped, right? And then square root of 3/1 is just square root of 3, okay? So now that I have my original 6 done of 30 degrees, what I chose to do, instead of recalculating everything using the 60 degree on the triangle, I use my cofunction identities. So I know that sine of 60 is the same thing as cosine 30. So all I have to do is look up here at cosine 30, and that tells me it's going to be square root of 3/2, right? Cosecant of 60, I know is the same thing as secant of 30. So I look up here, secant of 30 is 2 square root of 3/3. Okay. I know that tangent of 60 is the same as cotangent of 30. So I find cotangent of 30, and that's square root of 3. And then cotangent of 60 is the same thing as tangent of 30. So I go up here to tangent of 30, and this should be square root of 3/3. So to me, this was an easier way to do it. If it was easier for you to go back and use the triangle and recalculate all the values using the 60-degree measure, that's totally fine too. You'll get the same answer, okay? All right, so hopefully that gives us a little insight, okay? Again, we are going to need to know how to draw and label a 30, 60, 90-degree triangle. The other triangle that we're going to be using a lot in this class for reference is a 45, 45, 90 triangle. Okay, so this one is an isosceles triangle, right? An isosceles triangle has two sides of equal length. So you can see here we have one, and then our hypotenuse is the square root of 2. Now this one, we didn't have any unknown values to find, but we can still validate that this is square root of 2 if we wanted to do the Pythagorean theorem, right? If I didn't know that hypotenuse length, I would still square and add together the lengths of my triangle, the legs of my triangle, right? So I'd get 1 squared plus 1 squared equals, you know, whatever my hypotenuse squared is. So 1 squared is 1, 1 squared is 1. So that means my hypotenuse squared has to equal 2. And then to get rid of that square, I take the square root. Okay. So this is not something I would have you do. I'm just validating that the hypotenuse length is square root of 2. Okay. So here it says, why would a triangle with sides length 1 unit have a hypotenuse length? Oh, I just did what I should have done here, right? So to find this, we just use the Pythagorean theorem. Okay. Which we already did. Okay. Use the Pythagorean theorem. A squared plus b squared equals c squared. Okay. Now again, I'm not going to make you label those, but again, this is the triangle that you are going to have to remember the lengths on. Okay. So the good news is, look, both of these angles are 45. The other one we had 30 and 60, so we had to do trig functions for 30 and trig functions for 60. But here, both of these are 45, so we really only have to do it once, right? Because whatever we get using this angle would be the same thing we would get using this angle, okay? So notice opposite my 45 is 1, adjacent my 45 is 1, and then my hypotenuse is square root of 2. Okay. All right. So let's go ahead and define our trig function values for a 45-degree triangle. Sine, we can use our SOHCAHTOA, right? Sine is opposite over hypotenuse. So opposite is 1. Hypotenuse is square root of 2. So 1 over the square root of 2. My math lab won't like it like that, so we are going to go ahead and rationalize the denominator. So square root of 2 over square root of 2 gives me square root of 2 over 2. Okay. And then now that we have our sine value, we can go ahead and just do the reciprocal to get cosecant. Now, when I do the reciprocal, I don't use the simplified after the rationalizing answer. I use the original. So if I have 1 over square root of 2 and I flip that, that gives me square root of 2 over 1, which is just square root of 2. Okay. All right, I am going to go ahead and let you guys do the remaining 4. Go ahead and find cosine, secant, tangent, and cotangent. And then when you're ready, play the video again and we'll go over them. Okay, so let's go ahead and see how you did. When we do adjacent over hypotenuse, we actually should get the exact same thing as when we did opposite over hypotenuse, right? Because notice our adjacent side and our opposite side have the same value, right? So again, for cosine, we should get square root of 2 over 2. And then if we flip our original one, right, our secant should give us square root of 2. And then our tangent, which is our TOA, opposite over adjacent, we're getting opposite over adjacent. So 1 over 1, which is 1. And when we do the reciprocal, we still get 1. Okay. All right, so now we have our 2 reference triangles. So at any given point, if I tell you to draw and label either a 30, 60, 90 triangle or a 45, 45, 90 triangle, that is something you should be able to crank out pretty quick. Okay, so you need to have that on a note card or have that handy, to where you can reference it really quickly. It's also something you should be able to write down on an exam without having to look it up, because you're not going to be able to use notes and stuff on an exam, okay? Okay, so let's move on. Now for this, I just want to make sure that we understand the behavior of our trig functions as our angle increases from 0 degrees up to 90 degrees, because we're just talking about acute angles, right? So they're between 0 and 90 degrees. And this is actually going to help us kind of prove or disprove certain statements. So let's think about if we're talking about an angle theta that's going from 0 to 90 degrees. So that means we're going from 0 up to 90 degrees like this, okay? So let's think about what happens as we go in this direction, okay? Now remember our R value, our hypotenuse, is what creates that triangle, right? So right here, if I go out a distance of R, this would be the point R0, right? And then if I go up, say, to 30 degrees, notice my XY value here. What happened? Going from 0 degrees up to 30 degrees, let's think about this in terms of X and Y, okay? If this is my X value, as I go up to this next point, is my X getting bigger or smaller? Okay, right now my X is here. When I go up to this next value, notice now my X is here, right? And if I keep going, let's say I go up to 60, now my X is here. So as I open up that angle, right, as I start to rotate that hypotenuse or that terminal side of my angle, what's happening is my X values are getting smaller, right? They're getting closer and closer and closer to 0. So I'm just going to write here, X is getting smaller. Okay, so as I go from 0 degrees up to 90 degrees, my X's are getting smaller, right? So now let's think about what's happening with my Y's, okay? So let's look at my Y values. When I start here at 0, my Y value is here at 0, right? But when I move up to 30 degrees, now my Y value is up here, right? And then when I move up to 60 degrees, now my Y value is up here, right? And then if I move up to 90 degrees, my Y value is right here. So what happens as I increase this angle measure, notice my Y values are actually getting bigger. They're going up the Y-axis. So Y's getting bigger. Now I'm doing all of this to explain something to you. I'm not going to have you work this out, okay? This is just like a deeper thinking type thing, okay? So I want to think about, now that I know what's happening to my X's and my Y's, I should be able to relate that to my trig function values, okay? So let's look at sine. Remember, sine is Y over R, okay? So let's first look at the behavior of the numerator. So the numerator is Y. So let's think about what's happening to Y as we increase from 0 degrees to 90 degrees. Well, we already wrote over here, Y's are getting bigger. So that means the numerator values are getting larger, larger and larger and larger, right? Let's look at the behavior of the denominator. The denominator is R. And notice, no matter where I go, I'm just swinging that R value around, right? I'm keeping the same radius length all the way around. I'm not changing it. So R stays the same. So let's think about this fraction. If the top of the fraction is getting bigger and bigger and bigger, and the bottom is staying the same. So let's just pick a random number and think about this for a second. Let's pretend the bottom's 2, okay? And it's going to stay the same. And let's say the top's getting bigger. So maybe we start with 1 over 2, and then 2 over 2, and then 3 over 2, and then 4 over 2, 5 over 2, 6 over 2, 7 over 2, blah, 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 right? So if the top of a fraction gets big and big and big and big and big and big and big, and the bottom's not changing, what happens is that the overall fraction value is getting bigger and bigger and bigger, right? So the overall behavior here is increasing. Increasing, okay? So that means my sine values, as my angle gets bigger from 0 to 90 degrees, my sine values should be getting bigger. Does that make sense? So if I want to compare two sine values, let's say I want to compare the sine of 0 to the sine of 60, 60 should have a bigger sine value than 0 because 60 is a bigger angle, and we know that as our angles get bigger, our sine values get bigger. Okay, so this is just a helpful thing to know in the back of our mind. Okay, so now let's look at cosine. Let's see if cosine also increases as the angle increases. Okay, so cosine, remember, we calculate using x over r. So let's first look at the behavior of the numerator. So the numerator is just x. So as we increase our angle measure from 0 up to 90, right? What's happening to our x's, we wrote out here, is that our x's are actually getting smaller, right? They're decreasing. So the top of my fraction is getting smaller, and the bottom, which is my radius, is still staying the same. Stays the same. So now let's think about what that does to the overall fraction, right? If we have the top of the fraction that's getting smaller and smaller and smaller, and the top is staying the same, the bottom's staying the same. Let's say the bottom is like, I don't know, 10, right? And we're in the top of our fraction, say we have 9/10, and then we go to 8/10, and then we go to 7/10, and then we go to 6/10, and 5/10, and 4/10, and 3/10, and 2/10, and 1/10, right? So as the top of the fraction gets smaller, the overall value of the fraction gets smaller, right? So cosine actually ends up decreasing. Okay, so this is helpful because now if we want to compare two cosine values without even needing to calculate what they are, we should be able to determine which one's bigger just by looking at the angles. So if I want to compare, say, the cosine of 30 degrees to the cosine of 60 degrees, well, if I know that cosine is a decreasing function, then when I look at these two, since 60 is bigger, a bigger angle value, that means that its cosine is actually going to be smaller, right? Because decreasing means as the angle measure increases, our cosine values get smaller. Does that make sense? Okay, so let's look at tangent. Tangent's a little bit tricky because it has an x and a y. There's no value that's staying the same. Okay, so I'm going to think of this in a different way. I'm going to think of this as y times 1 over x. Okay, so if I think about this as y times 1 over x, I want to think about what is the top doing and what is the bottom doing, or what are these two pieces doing. Okay, so we know that our y are getting bigger, right? Our y's get bigger and bigger and bigger and bigger and bigger. So let's look at our y's getting bigger. That means they increase. And now I want to look at 1 over x. 1 over x. Is that going to get bigger or smaller? So let's think about what x is doing. X is actually getting smaller, right? So x, let's say it starts at 10, and it's going to go to 9, and it's going to go to 8, and it's going to go to 7. So if x is getting smaller, let's think about what that does to 1 over x. If x is getting smaller, let's say we start at 10, then we'd have 1 over 10. And then it gets smaller. 1 over 9, 1 over 8, 1 over 7, 1 over 6, 1 over 5. So what's happening to this little fraction, as the bottom gets smaller, the fraction actually gains more value, right? 1 over 10, if I then change it to 1 over 9, well, 1/9 is bigger than 1/10, right? If I keep going down, 1 over 5, 1 over 4, 1 over 3, 1/2, right? This value is getting bigger and bigger and bigger. So 1 over x gets bigger. Okay. So if I have something that's increasing times something that's getting bigger, the whole entire thing is going to be increasing. Okay. Again, I'm not going to have you prove this whole chart. This is just our thinking it through strategy so that we know the behavior of each of these trig functions. Okay. All right. So what we've learned so far is that as we go from 0 up to 90 degrees, our sine and our tangent values increase. So as the angle measure gets bigger, so does the sine and the tangent value. With cosine, though, as our angle gets bigger, our cosine value gets smaller, right? So now we want to look at, well, what does that mean for our inverse functions, right? So instead of looking at the numerator and the denominator, I'm going to use the idea that these are reciprocals of the ones we've already figured out, okay? So let's think about this. If sine theta is increasing, okay, I'm just going to use an arrow up to show it's increasing, then I can think of cosecant theta, right? This is the same as 1 over sine theta, right? It's the reciprocal. So if I think of sine getting bigger and bigger and bigger, then 1 over sine theta is getting what? What is it getting? If sine theta gets bigger and I stick it in the denominator, then this fraction is getting what? Let's think about sine getting bigger. So let's say sine is like 2, and then maybe it's 3, and then maybe it's 4. So if I have 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, the value of this is actually getting smaller, right? Going from 1/2 to 1/3 is actually making the value less. So if the denominator of the fraction gets bigger, the whole value of the fraction is actually getting smaller. Okay. So if the whole value of the fraction is getting smaller, then that means that our cosecant function is actually decreasing. Okay. And by the same theory, right, the same thinking, I can do the same thing for secant and cotangent, right? Secant is the same thing as 1 over cosine theta. So if cosine theta is, notice we found that cosine was decreasing, cosine theta is decreasing or getting smaller, then 1 over cosine theta is getting, what do you think? If the bottom of the fraction gets smaller, the bottom of the fraction gets smaller, so maybe we're going from like 1/7 down to 1/3, down to 1/2, right? What's happening is as the bottom of the fraction, as that number gets smaller, it actually makes the whole value of our fraction bigger, right? Going from 1/7 to 1/2 is actually increasing it, right? So it gets bigger. So this would be an increasing function. Okay. And then cotangent, same idea. If tangent theta is increasing, then 1 over tangent theta is getting the opposite, right? Smaller. So this is going to be decreasing. Now, there's all these mathematical equations to help us remember this, but really all we have to remember is the first 3. If we know that sine, tangent are increasing and cosine is decreasing, then their inverses do the opposite, okay? All right, so I'm going to write out what this means in some like verbiage we can maybe understand. But I think I'm going to do it on the first page. I mean, on the next page, because we're going to use it on the next page. Okay. All right. So let's think about this. Let's say we have 2 angles. I'm just going to call them alpha and beta. Let's say we know that alpha is smaller than beta. Okay. Alpha is the smaller angle. Beta is the bigger. Then we know that sine, the sine function, should get bigger as the angles get bigger, right? So that means that sine of alpha should be less than sine beta, right? Smaller angle has smaller sine value because we know that the sine function increases as the angle increases. Same thing with tangent, right? If we have alpha is less than beta, then tangent alpha is less than tangent beta. This is just our math way of writing these things, right? So if alpha is the smaller angle, then tangent alpha should be the smaller tangent value. Okay, same thing with sine. But cosine, right? Cosine is the opposite. If alpha is less than beta, then cosine decreases, meaning that cosine alpha is going to be bigger than cosine beta. Okay? Now, we could write out these mathematical statements for all 6 of them, but I'm just going to use the first 3. Okay? All right, so here's our problem. It says indicate whether the following statements are true or false and then explain. So what I want to do is I want to kind of use this reasoning of if I know the first angle is smaller than the next one, then I should know the behavior of the trig function, right? So I'm going to go ahead and just rewrite this with the smaller angle first, right? So I want to write it as 23 degrees is less than 25 degrees, right? Well, that's true. And so what we know about tangent is that tangent is increasing. So that means that tangent 23 degrees should be less than tangent of 25 degrees, right? So I just want to double check that this is what my statement's actually saying. Now this one has it written in the reverse order, so let's just rewrite it. I want to rewrite it with the tangent 23 first so I can see if it makes this correct statement. So if I write this with tangent 23 degrees, notice the way this inequality symbol is written, it's opened up to the 23. So if I spin it around, it still needs to be opened up to the 23. So I have tangent 25 degrees. So what this is saying is that tangent of 23 degrees should be greater than tangent 25, which we know is false. Okay? It's false because we know the tangent values should increase. Tangent values should increase. Okay? So I always like to write what the true statement should be based on whatever function we're dealing with. And then once I know this is the true statement, right? This is what I know to be true, then I just check to see, is that what this problem is saying? And if it is, then I say it's true. If it's not, then I explain why it's not true. Okay? So let's look at the next one. This one says cosecant of 44 degrees is less than cosecant 40 degrees. So I'm just going to ignore that, and I'm going to write what I should know about cosecant. Okay, so first of all, the degree measures that I'm dealing with is 40 degrees and 44. So I know that 40 degrees is less than 44 degrees should imply something about cosecant. Now let's think about cosecant. Cosecant is the inverse of sine, right? Now sine increases and its inverse does the opposite. It decreases. So that means that cosecant of 40 degrees, if it's a decreasing function, this one should actually be larger than cosecant 44 degrees, right? As my angle measures increase, the values get smaller, okay? So this is what I know to be true off of the last page that we just determined, right? So now I want to determine, is this what my problem is saying? Okay, so I'm going to rewrite it so that the smaller angle comes first. So cosecant 40 degrees. Notice it's open to 40 degrees here. So when I rewrite it, it still needs to be open to 40 degrees. And then I have cosecant 44 degrees. So when I compare what my problem says to what I know to be true, notice it's the same. So I can just say this is True. Yay. Okay. All right, I have one more problem type I want to show you, and then that will be the end of this section. And I know we did this before, but it's been a hot second, so we're just going to look at doing it again so we don't forget about it, okay? This example is asking us to find the equation of the line. Anytime it asks you to find the equation of the line, you should be thinking y equals mx plus b, okay? So we need to find the equation of the line that is collinear with the terminal side of a 30-degree angle. Collinear means that the terminating side is the same. Okay, so notice this is a 30-degree angle. This is the terminating side or the terminal side of my angle. So basically what we're looking for is the equation of this line right here. Okay, this line that acts like the terminal side. This is the line we are looking for. Okay, so all of this was just to say we're using the terminal side of a 30-degree line, and that's the line we're looking for. Okay, so we need to know two things. We need to know our B, right? And remember, B is just our y-intercept, 0b, right? So if I look at this line, I can easily see what our y-intercept is. Right? Our y-intercept on this line is just the point 0, 0, right? Or in other words, b equals 0. So that's going to be easy enough. And then I also need to figure out my slope, right? M is our slope, which is our rise over our run, okay? So if I look at our rise over our run, right, or our opposite over our adjacent, that's actually our tangent value, right? That's going to give us the tangent of 30. Just FYI, don't really need that in there, but I'm going to put it in there anyways. So opposite, our rise is 1 over our run, which is square root of 3. So that gives us our slope. And then again, we want to make sure that we rationalize the denominator. So I'm going to go ahead and just multiply by square root of 3 on top and bottom. So that gives me square root of 3 over 3. So now that I know my b value and I know my slope, I should be able to write the equation of the line. So y is equal to my slope, which is square root of 3 over 3x, plus my b value 0. And since my b value is 0, I don't really need to write it. So we just get y is equal to the square root of 3 over 3x. And that's the equation of the line. Okay. All right, so that is the end of section 2.1. You should now be able to go ahead and complete that assignment. If you have any questions, please let me know. I'm back. Just kidding. There was one more little thing. On the very back page here, on page 8, this is just a little spot for you to be able to see if you can draw and label the 30, 60, 90 triangle and the 45, 45, 90 triangle. So I encourage you to pause the video and without looking back at your notes, see if you can label it, right? So I would just draw it. Here's my 30, here's my 60, here's my 90, right? And then you can say this is your 45, 45, 90, and see if without looking back at your notes, you can label the sides of these triangles. Okay, go ahead and do that real quick and then check yourself back in your notes, or you can unpause this video and see if you got it right. I'll go over it in just a second. All right, so on the first one, 30, remember with a 30-60 triangle, we have 1, 2, square root of 3 is our side lengths. So opposite 30, which is our smallest angle, should be our smallest side. Opposite our largest angle, which is 90, should be our largest side. And then opposite 60 should be that middle value, which is square root of 3. Okay, 45, the two legs that are attached to the 90-degree angle have length 1, and our hypotenuse is square root of 2. So I hope you got those. Okay, now you can do your homework for this section.